Hello students, and welcome once again to my engineering physics channel. This is Sanjeev Bade from KJ Somaya Institute of Engineering and Information Technology. This is our session number 4 on a special theory of relativity, and in this session we are going to get introduced to the concepts like time dilation, length contraction, concept of relativistic mass, and then we will try to get the famous mass energy equivalence relation E is equal to mc square. For understanding all these concepts, we will use the Lorentz transformations which we have discussed in the session number 3. So if you have gone through the session number 3, then only you are going to understand this session number 4. So if you have not gone through the session number 3, then please go through, in fact through all the sessions, session number 1, 2 and 3. Time dilation. In order to understand the concept of time dilation, let us consider two inertial frames of references, frame S and frame S prime. Let us say that frame S prime is moving with velocity v with respect to frame S. In both frames we are provided with the clocks which give accurate timing. So the clocks are perfectly fine. There is no problem with the clocks provided in each of the inertial frames. Now let us ask the observer in frame S to measure some time interval. The observer in frame S will measure that time interval as delta t, which is equal to the difference between two time instances noted by him, t2 minus t1. If you ask the observer in frame S prime to measure the time interval, he will measure it as delta t prime, which is equal to t2 prime minus t1 prime. He is trying to measure the same time interval. According to Lorentz transformation, we can write t2 prime equal to t2 minus vx by c square upon square root of 1 minus v square by c square, and t1 prime equal to t1 minus vx by c square upon square root of 1 minus v square by c square. We can find the time interval measured by an observer in frame S prime, delta t prime, which is equal to t2 prime minus t1 prime. We can get it as t2 minus t1 upon square root of 1 minus v square by c square. T2 minus t1 is nothing but the time interval measured by an observer in frame S. So we can write delta t prime is equal to delta t upon square root of 1 minus v square by c square. What we can note from this is, even though the clocks in frame S and frame S prime are perfectly fine, the observer in frame S is measuring the time as delta t, and the observer in frame S prime is measuring the time interval as delta t prime, which is equal to delta t upon square root of 1 minus v square by c square. Means the time intervals measured by the two observers in two different inertial frames are not same. So this is called as the time dilation. Observer in frame S will say that my time interval measured is perfectly okay, but observer in frame S prime is measuring the time slowly, and observer in frame S prime will say that my time interval measured is okay, and the observer in frame S is measuring the time slowly because his clock may be running slowly. Now in this relation, let us see what happens when we put v to be very much less than c. Means that when frame S prime is moving with very less velocity as compared to the velocity of light. So in that case, just look here. V square upon c square. If v is very much less than c, then v square upon c square can be neglected, and we can write delta t prime to be equal to delta t. So if the frames are moving with comparatively lower speeds, then there is no time difference in the time measured by the two observers in two different frames. But if v is comparable to c, then this cannot be neglected, and then delta t prime will be different from delta t. This time dilation introduced one concept which is used in many of the science fictions. For example, if a person is making a journey into space in a high speed rocket which is moving with velocity comparable to velocity of light and returns back on earth after some years, then his age will not increase much in comparison with people on earth. But the discussion that we did, in our discussion both the frames S and S prime were inertial frames, but in this example of the person making a journey into the space and coming back, and if you see the other frame of reference is on the earth, in this case both the frames will not be the inertial frames, and another theory will be needed to explain this phenomenon. You can get more insight on this problem on this particular site. Now let us solve some problems based on time dilation. First problem: an experiment is performed in a laboratory moving at speed 5 into 10 raised to 7 meter per second. If the time required to complete the experiment is 1.013 into 10 raised to minus 6 seconds, find the time measured to complete the experiments in a laboratory at rest. So in this problem, the time measured in the moving laboratory is given as 1.013 into 10 raised to minus 6 seconds. So delta t prime is given. We can write delta t prime to be equal to delta t upon square root of 1 minus v square by c square, relation for time dilation. Delta t prime is given, so we can substitute it. V is given 5 into 10 raised to 7, c we know 3 into 10 raised to 8 meter per second, and we can calculate delta t to be 9.9 into 10 raised to minus 7 seconds. So the time measured to complete the experiment in laboratory at rest will be 9.9 into 10 raised to minus 7 seconds. Let us move to the next problem. At what speed does a clock move if it runs at a rate which is 1/2 the rate of the clock at rest? So here we have a frame S prime which is moving with velocity v. The observer in frame S prime is measuring the time as delta t prime, and the observer in frame S is measuring the time interval as delta t. Time dilation relation gives us delta t is equal to delta t prime is equal to delta t upon square root of 1 minus v square by c square. It is given that a clock in frame S prime is running at half rate of the clock in frame S. So we can write delta t prime equal to 2 into delta t, and from this we can just get the value of v as square root of 3 by 4 c, which is 0.866 c. So this was a simple problem again based on time dilation. Under Galilean transformation, we have seen that the length of the rod in the two inertial frames of reference S and S prime do not change. Let us see what happens to the length of the rod when we consider the Lorentz transformation. Let us consider again two inertial frames S and S prime. Let frame S prime is moving with relative speed v with respect to S in x direction. Let us try to measure the length of the rod. In frame S, the observer will say that length of the rod is L, which is equal to x2 minus x1, where x2 is the position of one end of the rod and x1 is the position of the other end of the rod. an observer in frame S prime will note the location of the ends of the rods as x2 prime and x1 prime, and therefore this observer in frame S prime will say that length of the rod is L prime, which is equal to x2 prime minus x1 prime. Now according to Lorentz transformations, we can write x2 prime to be equal to x2 minus vt upon square root of 1 minus v square by c square, and x1 prime can be written as x1 minus vt upon square root of 1 minus v square by c square. Now if you calculate L prime by using these Lorentz transformations, we can get it as x2 minus x1 upon square root of 1 minus v square by c square. x2 minus x1 is nothing but the length measured by an observer in frame S. So the length measured by an observer in frame S prime is not same as the length measured by an observer in frame S. They are related by the relation L prime equal to L upon square root of 1 minus v square by c square. This is called as length contraction. So if an observer from one frame which is at rest is observing some object in another frame which is moving with some velocity v, then he will find that length of that object is reduced. So this phenomenon is called as length contraction. Now what will happen when v is very much less than c? Means the frames are moving with very small relative speed. If v is very much less than c, then v square by c square can be neglected, and we can write L dash to be equal to L. So it leads to Galilean thing, means the lengths are same. Lengths measured by the observers in different inertial frames will be same. In what case? When v is very much less than c. But when v is comparable to c, v is very close to c, then this is not the case, and the lengths measured by the observers in different frames of references will be different. So this is the relation for length contraction, L prime equal to L upon square root of 1 minus v square by c square, and here there are some examples. If the train is at rest, then its length measured by the observer you can see, and when the train is moving, the length measured by the observer will be smaller. This is another example. This is a circle, and as the velocity of the circle goes on increasing, the length of that, the diameter of that circle goes on reducing. So this is a phenomenon which is called as length contraction. Now let us solve some problems based on this length contraction. First problem: a rocket ship is 100 meter long on the ground. When it is in flight, its length is 99 meter to an observer on the ground. What is its speed? A simple problem, straightforward one. L is given as 99 meters and L prime is given as 100 meters. So we can calculate velocity from this by just simply substituting the values. C is taken as 3 into 10 raised to 8 meter per second here, and we can calculate velocity v. In this problem it comes out to be 4.23 into 10 raised to 7 meter per second. This is another simple problem. A rocket ship which is 100 meter long on the earth is moving with velocity 0.9 c. What will be its length measured by an observer on the earth? So here L prime is given as 100 meter, and when the rocket ship starts moving with the velocity equal to 0.9 c, we are asked to find its length. So its length will be 43.58 meters. After understanding time dilation and length contraction concept, now let us move ahead to mass energy equivalence. To understand this mass energy equivalence, we need to know the concept of relativistic mass first. In Newtonian mechanics, momentum is given by P equal to m naught v, where m naught is rest mass of the body, and the energy is given by E equal to E naught plus 1 by 2 m naught v square, where E naught is rest energy which was undetermined in Newtonian mechanics. In special theory of relativity, the mass of the body depends on the velocity. It is not constant. It depends on the velocity, and the relativistic mass is given by m equal to m naught upon square root of 1 minus v square by c square. So this term square root of 1 minus v square by c square, which we have seen in time dilation relation, length contraction relation, is appearing here also. Relativistic mass is given by m naught upon square root of 1 minus v square by c square. You can see the relativistic mass is always greater than the rest mass. The rest mass m naught will be same in all inertial frames of references, but the relativistic mass is different in different frames. If you put v equal to c, then the relativistic mass will become infinite, and therefore it is not possible for any object to attain the velocity which is equal to velocity of light. Now let us see how Einstein arrived at his mass energy equivalence relation. We know the force is defined as the time rate of change of momentum. So we can write F is equal to d by dt mv. Let us call this as equation number 1. The kinetic energy of moving particle is defined as the work done in accelerating it from rest to its final speed v. So if you find the kinetic energy of a particle when the particle is displaced by some distance s, we can write this kinetic energy to be equal to integration from 0 to s f ds. Now f being the force equal to d by dt mv. When the distance covered by the particle is s, it will reach the velocity v, and therefore the relation for kinetic energy becomes integration from 0 to v d mv equal to integration from 0 to v d. M is replaced by m naught upon square root of 1 minus v square by c square. So here we are writing the relativistic mass m equal to m naught upon square root of 1 minus v square by c square. Integrating by parts, we can get Ek, kinetic energy, to be equal to m naught v square upon square root of 1 minus v square by c square minus m naught integration from 0 to v dv upon square root of 1 minus v square by c square. So this is the last step in the earlier slide. So the kinetic energy can be written as m naught c square upon square root of 1 minus v square by c square minus m naught c square. This can be written as mc square minus m naught c square. M naught upon square root of 1 minus v square by c square is written as m, the relativistic mass. You can take m naught c square common from this both the terms, and we can write kinetic energy equal to m naught c square into bracket 1 by square root of 1 minus v square by c square minus 1. Now using binomial theorem, we can write 1 by square root of 1 minus v square by c square to be equal to 1 plus v square by 2c square plus 3v raised to 4 by 8c raised to 4 plus and so on. At lower speeds, when v is very much less than c, the higher terms in this can be neglected, and we will be left with only 1 plus v square by 2c square, and therefore the kinetic energy can be written as m naught c square. This is replaced by 1 plus v square by 2c square minus 1. 1 will get cancelled, and what we will get is 1 by 2 m naught v square. So this is a classical relation. So at lower velocities, what we get is kinetic energy is equal to 1 by 2 m naught v square, a classical relation. This equation, equation number 3, can be written as mc square to be equal to kinetic energy plus m naught c square. So here E is the energy, which is equal to mc square, and E naught can be written as m naught c square. These are known as mass energy equivalence relations. So now some simple problems based on mass energy equivalence relation. Calculate the speed at which the mass of an electron becomes 4 times its rest mass. So given that m is equal to 4 times its rest mass, we know m is equal to m naught upon square root of 1 minus v square by c square. So 1 minus square root of 1 minus v square by c square is equal to m naught upon m, that is 1 upon 4, and it can be easily solved, and we can get the speed of electron as 2.904 into 10 raised to 8 meter per second. So when the speed of electron is 2.904 into 10 raised to 8 meter per second, its relativistic mass will become 4 times its rest mass. Next problem. Calculate the speed of particle whose total energy is twice its rest energy. So in this problem, given that total energy mc square, total energy is E is equal to mc square, is equal to twice its rest energy. Rest energy is E naught. So E is equal to 2 E naught. So mc square is equal to 2 m naught c square. This is the given thing. C square will get cancelled. M is equal to 2 m naught will remain. So m is equal to m naught upon square root of 1 minus v square by c square. So here again m naught will get cancelled, and we can write 1 minus v square by c square equal to 1 upon 4. Again here we can solve it to get the value of v. So speed of particle calculated is 2.5984 into 10 raised to 8 meter per second in this case. These are the references that I have used to prepare this lecture. So we are at the end of this session on special theory of relativity. I hope you must have enjoyed this session, and you must have got answers to many unanswered questions in your mind. If you like this session, then please subscribe to the channel so that you will get timely intimation of new videos uploaded to the channel. If you have any doubts, if you have any queries, please write in the comment section, or you can directly mail me on my mail ID. Mail ID is available on the channel description. So thank you once again for watching.